Hello. So this video today is going to be looking at gravitational force between two different bodies or two different masses. As you can see here, we're using Universe Sandbox just because it allows me to very easily adjust the masses and various other variables of the planets altogether. So, we've got the a view that you're probably familiar with, the Earth and the Moon. As we know, the Moon orbits the Earth. So, if it's all good as is, what however happens if we double the mass of the Moon? So up here in the corner I can adjust what the mass is. So if we go and if we go and double that, what's going to happen? Have a think about it. Feel free to pause the video and think about it. But yeah, have a think about what's going to happen when I double it. And now I will. There we are. Now I'm just going to speed things up a bit because otherwise we're going to be sitting here being very, very bored. So there we are. Now you'll notice, one, the orbit is a little bit different. But you'll also notice the Earth is starting to move as well. Now, if there's more motion, what we can probably conclude is that there are more forces at play, or at the very least, more unbalanced forces at play. So, how then does that make any sense at all? Well, simply put, you have a gravitational force between objects. So if we just switch over to working and stuff. So here what we've got is we've got the working for what the gravitational force between the Earth and the Moon is normally. Now, do understand, and I apologize for the probably bad circle I'm about to draw. We've got that. So let's say that's the Earth, and then you've got the Moon somewhere along its orbit. Now, there's going to be gravitational force coming from both of these towards each other. Because, if we remember correctly, for every for every reaction force, there's an equal and opposite reaction force. And this follows the same kind of idea. If something is being pulled towards something else due to gravity, the thing that it's being pulled towards is also being pulled towards it. So, for example, we exert a gravitational force on the Earth, much like the Earth exerts a gravitational force on us. The difference is we're very, 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 very small, so the gravitational force exerted on us to keep us there is a barely noticeable gravitational force to the Earth. It wouldn't even slightly move it. On top of that, you've got people all over the world sort of cancelling it all out as well. So that's you can pause the video and sort of have a read through that. That is the working for figuring out the gravitational force if the Earth is the same mass as normal and if the Moon is the same mass as normal. So if we get rid of all that though, let's try and figure out what this new force is going to be. Now, just as a reminder, the normal force between them was 1.98 times 10 to the 20 newtons. And that was the normal force between them. The normal gravitational force between them. So now, what we can do, so we use the equation F is equal to G, so the gravitational constant, I think Newton figured that one out, G times mass 1 times mass 2 divided by the orbital radius squared. So, let's write down what we know. So we know G from up above is equal to 6.67 times 10 to the negative 11. I'm not going to write all the units because it's up here and it's long and messy. Then we have mass 1. So we'll go with the Earth's mass is mass 1, which, as we can see above, is 5.97 times 10 to the 24 kilograms. Then we have mass 2, which is equal to the Moon's mass, which is now double, because we doubled that. So that's 7.35 times 10 to the 22 all times 2, which is equal to 14.7 times 10 to the 22 kilograms. Then we have the radius, which that stayed the same. No, we just want radius by itself. The radius, which is 3.85 times 10 to the 8 meters. So from the center of the Earth to the center of the Moon is, and I say approximately because it's been rounded to 3 significant figures, is approximately 3.85 times 10 to the 8 meters, which is the same as 385 million meters. So we've got all our variables that we know written down, and we're trying to figure out the force, so that's our question mark. So now we can plug those numbers in. So 6.67 times 10 to the negative 11 times, I'm just going to move this stuff a bit so that I have a bit more room. Actually, might even make it a bit smaller. There we are. So we'll put that up in the corner. We've got our variables recorded. And so we've got 6.67 times 10 to the negative 11 times 5.97 times 10 to the 24 times 7.35 times 10 to the 22. Sorry, I was reading the non-adjusted number. So 14.7 times 10 to the 22, all over 3.85 times 10 to the 8, all squared. There we are. Now this looks like a horrible, horrible mess, but it can be simplified reasonably easily. So we end up having, the best idea to do is get all of the times 10s by themselves. So we have 6.67 times 5.97 times 14.7 times 10 to the negative 11 times 10 to the 24 times 10 to the 22. And now on the bottom we have 3.85 squared, because if you have two numbers multiplied together and they're squared, you can separate them out and just have them each individually squared. Can't do it if it's adding them together, but if it's multiplying, you can. So then we have the times 10 to the 8 squared, but if you've got a number to a power and you then put that to a power, you just multiply together the two powers. So in this case, 8 times 2 is 16. And what we can do, if it's on the top, the powers add together. If it's on the bottom, they subtract. So we end up getting negative 11 plus 24 plus 22 minus 16, which is then equal to, so 24 plus 22, I could do this with a calculator, but it's always handy, I find, to be able to do things this way. No, not a 6, that's a 46. Then we have the 11 and the 16, which I can actually do in my head, it's 27, but there, and then we have 46 minus 27, so that ends up going to be 3, that's 1, that's 9, that's 19. So that simplifies the whole powers of 10 thing. So we have 6.67 times 5.97 times 14.7 times 10 to the power of 19. All divided by 3.85 squared. Now at this point, you're probably best off throwing the numbers into your calculator. So I've got a calculator, you won't be able to see it, but I'm just going to quickly do the numbers. So 6.67 times 5.97 times 14.7. I'm just doing sort of top and bottom separately. So we have 585. Now you use unrounded values whenever you're doing the working. 35253 times 10 to the 19 all over 3.85 times 3.85, which ends up being 14.8225. And now in the calculator we just take these two numbers and we so we do the 585.35253 divided by 14.8225, and that ends up being 39, and this is where we round, well, we put in an unrounded value, 39.4908 times 10 to the 19 newtons. And then we adjust it for rounding. So we'll take the three most significant figures, which will be the 3, the 9, and then the 4 rounds to a 5. And one other thing, and this will make sense when you look up at what the normal force would be for this kind of thing. If we move this decimal point up by 1, so we end up having 3.95, then we increase the power of 10 by 1, so we then have times 10 to the 20 newtons. Now we can say that that is approximately, and if there were no rounding it should be exactly, 1.98 times 10 to the 20 all times 2, which is about right, because 1.98 times 2 would end up being 3.96. So it is pretty close, and we can see that we doubled the mass, the force doubled. If we think about that in regards to the orbit that's happening, we can see now that that increased force means that now that force is actually having an effect on the Earth itself. However, if we go and we reset it, now what happens if instead we double the size of the Earth? Some of you may have already figured out how this all works, but it's best to just sort of go through it. So if we make that 2 Earths, think about what that's going to do. And here we go. And if we speed it up again, so that it's not super slow. Now, you're getting, well, for one, a bit of a weirder moon orbit. You're still getting a bit of movement on the Earth, but the moon is moving more. It's like getting a lot closer to the Earth. Now, if it's getting closer to the Earth, that suggests there's a greater force pulling it there. And as we found with the moon, doubling its mass increased the force. So, if we go back to the working, let's move that like that. If we go back to the working, the only difference that has happened is instead of the moon's mass doubling, the Earth's mass has doubled. Which, if we have a look up here where we rewrote the moon's mass as original moon mass times 2, if we then change this into 5.97 times 10 to the 24 times 7.35 times 10 to the 22 all times 2, this is still the exact same calculation because we're multiplying the mass of the Earth. Now, if we think about the context of sort of how that then changes those orbits, the moon is still the same size, and so by doubling that mass, doubling that force, the moon is going to have a much larger effect. Because if we think about things like inertia and so on, the larger it is, the harder it is to move, and the harder it is to stop moving. And so this force has still been doubled, but the moon is its regular size, so it's getting pulled a lot stronger by the Earth. Then the Earth itself, it's double the mass, so it's a bit harder to move. However, that force is doubled, so there's still an effect on the Earth. On top of that, due to the nature of the weird elliptical orbit, that's also going to cause strange stuff to happen, just because those forces will fluctuate as that radius changes. But that's a whole different kettle of fish that you don't have to worry about. So basically the idea with this is that you can actually represent this whole equation and get the answer just by using the initial force value and then any multiples of what you've got. So, for example, if we have, so F equals G, and in this case I'm going to go ME for Earth and MM for Moon, and that's over R squared. Now that is equal to 1.98 times 10 to the 20 newtons. However, we can then go, okay, force G, and then 2 mass of Earth, mass of the Moon, over R squared is equal to 2 times 1.98 times 10 to the 20 newtons, which is equal to 3.96 times 10 to the 20 newtons. And again, we can go, well, okay, let's say we wanted to halve the mass of the Earth. We can then go, okay, a half mass of Earth, mass of the Moon, divided by r squared is equal to a half times 1.98 times 10 to the 20 newtons, which is equal to 0.99 times 10 to the 20 newtons. And that's half of it. And all of this, it works regardless. So if you're asked, someone wants to put up a satellite that is double the mass of a satellite with this amount of force, all you have to do is double it. If someone asks what would happen if you basically any different mass, you just take the multiplier of the mass and you multiply the original force by that much. Now the question is, what about the radius? Because the radius isn't just straightforward. If you end up having a situation where, let's say, you double the radius, the thing to remember is that doubling also gets squared. And as such, what's 2 squared? It's 4. So you're going to end up getting 1/4 of the original force just by doubling the radius. So increasing the radius decreases the that should be it. Increasing the radius decreases the force because it's further away, and as we know, if you're further away from something in regards to gravity, there's less force on you. A fun little fact is, if you're standing on the moon and directly above you is the Earth, if you jump, you'll be fighting less gravity than if you were on the other side of the moon at that point in time. It wouldn't be hugely noticeable. That being said, the gravity on the moon is relatively weak. I think it's about 1/3 of Earth. But it's an important thing to consider. So we've got all of these things, and we can think about all of this. But you probably want to be able to figure it out yourself. So if we have a look at this, now I know the top cornery bit is kind of covered up, so actually we might just change this to okay, we'll just give me a moment. What? What is it? Right. So if so this is a PhET simulator. and it'll allow you to basically do what I was doing in Universe Sandbox. Here we go. So you can just use a model. So if you use the model, you end up getting something that looks like this. You can get it to show the gravity force, and you can get it to show the velocity. Now, one thing to bear in mind, the velocity is always tangential to the gravity force. So what that means is it's always at a right angle, so if we press play, that's always at a right angle to the gravitational force. If it weren't at a right angle, you would almost certainly have it, no, it's always going to be at a right angle, it can't not be. So we end up having that. I mean, if we double the Earth's mass, we'll see that those arrows double in size. Yep, there we go. And if we half the Sun's mass, we'll see those arrows half in size. And in this case, the gravitational force is not enough to hold on, so therefore those arrows are getting smaller as the radius keeps getting bigger. You can also use to scale. So like before, when the Earth was going around the moon, the Earth was going around the sun, it wasn't entirely accurate to the actual scale that you're looking at. Everything was a bit bigger. Whereas here, that's actually sort of how far away the sun is. And this is quite nice. It can record how that path goes, records the forces and all of that. And you can change, you can have like the moon and the Earth all going at once. It gets a little bit messy with all three of those. You can also have that one, the moon and the Earth. And then the other one you can have is a satellite and Earth. However, do be careful of this one, because if you increase the size of the Earth, it destroys the satellite, unless you make sure to move the satellite. So you can select an object and you can move it. You can't do it with the central object, but as you can see, you can adjust its velocity. So so have a play around with that. Have a look at what happens when you double things, when you double masses, half masses, and do try to have a play around with the radius. So what I challenge you to do is, if you're going to change the mass, keep it paused and try to change the radius to be correct. I will point one thing out. You will also need to consider the velocity. So for that sake, I will just sort of show you how that would go. So basically the equation you'd be looking at to consider for this part, so we have F is equal to mv squared over r. So you're only dealing with one mass. So for example, if we did this for the moon, get the orbital velocity of the moon, we can go, so we know what force is. The gravitational force is 1.98 times 10 to the 20 newtons. Then we have the mass, 7.35 times 10 to the 22 kilograms, and the radius, 3.85 5 times 10 to the 8 meters. And we're wanting to figure out the velocity. So, easiest way in my opinion is just rearrange the equation first. You can also substitute numbers in first and then go from there. I'm quite comfortable rearranging and stuff, so that's what I would usually do. So you end up getting F times R because you multiply by R to get them on both sides. Then you divide by M to get the M on the same on the other side to the velocity. You have velocity squared, and because you've got the squared, you just square root it all to be F R over M all square rooted equals V. And so now we can just plug numbers in. So that's equal to the square root of, I'm going to need more room than that, 1.98 times 10 to the 20 times 3.85 times 10 to the 8 divided by 7.35 times 10 to the 22. I know this may seem a little bit going on and on and on, but it is important, and once you get to a point where this maths is sort of fine and makes sense, your life will be a lot easier. So we've got that. If we do the whole times 10 to the power of trick thingy that I showed you before, we've got a 20 on the top, we've also got an 8 on the top, and we've got a 22 on the bottom, which that's going to be 20 plus 8 is 28. That minus 22, well, the 20s cancel out, so it's 8 minus 2, which is 6. So it ends up being 1.98 times 3.85 times 10 to the 6 all over 7.35 all square rooted, which I'll just use the calculator, and again, sorry for not having that showing up, but it's 1.98 times 3.85, which is 7.623 times 10 to the 6 divided by 7.35. So it's going to be pretty close to 1 times 10 to the 6, which is quite nice. And that's going to give us, so 7.623 divided by 7.35 is equal to, yep, so 1.0371 times 10 to the 6 all square rooted, and so the square rooted value of that, so square root of 1.0, actually I can just go, yeah, so the square root of that, where's the button for that, square root, there we are, is 1.0184, and then the thing to consider, so a square root is a power of a half, therefore when you have something to the power of something, then to the power again, you multiply the powers, so 6 times a half is times 10 to the 3, and this is going to be meters per second. Now this is going to be tangential to the circular path, and so grand total of that, if we round it, is 1.02 times 10 to the 3 meters per second. So that's basically how fast tangentially the moon is moving. You can then sort of figure out more stuff when you get into rotational kinematics, but that will be all for now. So I do hope that was helpful, and yeah, have a think about how you can figure out how to get things like the velocity and the radius correct, so that the orbit doesn't go really wacky. So yeah, have a go with that, and I hope this was useful.